Alright, so in this video, we are going to be encoding um, the elementary row operations we may remember from E2 and encoding them as matrices and matrix multiplication. And so we're going to let A be some random 4x4 matrix, and we're going to compute two different row operations and the matrices that represent them, 1 n, where I replace R4 with itself minus 3 times the second row, and a matrix P that swaps the first and fourth row. So one thing I want us to always keep in the back of our mind is the identity matrix, right? The identity matrix is the matrix that has no action, right, on any products that we anything that we take its product with. And so what we want then is to use this as a baseline for how we construct each one of these matrices. So the first things first is I'm looking at the matrix N, where I'm replacing R4 with minus 3 R2 plus R4, basically, right? And so the first thing we want to note is that in this matrix, the first, second, and third rows of A will not be changed with this operation, right? And so since the identity matrix is the matrix which doesn't change things when we take its product, we want to use that to tell us what the first three rows are going to be. And there we go. Those are the first three rows of n. If I take at least those rows and multiply it against any matrix, at least the first three rows are not going to be changed. And it really is just the last row that I want to adjust. And so when I'm looking at n here, what I see is that, all right, I want, like, whatever A is, all right, I want to see what happens when I take this row against each of the columns of A. And I say, well, what I want is for there to be one copy of R4 and minus 3 copies of R2. And so I can encode that by one copy of R4 and minus 3 copies of R2. And I recommend taking some time to take this matrix N and multiply it against a bunch of different A's to see that in fact has this effect, or to refer back to the activities where we work through this. But another observation you may have is that this matrix N is exactly what you get if you take minus 3 times the second row of the identity and add it to R4 of the identity. That just so happens to be this N. Alright, so that's what N would be. Now if we take a look at what P ought to be, so P is the matrix that swaps the first and fourth rows. So if we want to swap the first and fourth rows, once again we observe that that would mean the second and third rows do not change. And that means that I can just encode, I can use the identity matrix's second and third rows to represent P not changing the second and third rows. Well, what do I want when I'm done in the first row of a matrix that I apply P to? I want the first row to be the fourth row. In other words, I want there to be one copy of the fourth row and no copies of any other row, right? And similarly, when I look at the last row of a matrix transformed by P, I want there to be one copy of the first row in the fourth row, and then everything else doesn't matter. And so that's P. And so you once again may observe that I can also obtain this matrix by actually performing these row operations, swapping row 1 and row 4 on the identity matrix. Alright, and so if I am looking at a situation where I have a matrix A, I want to first apply swapping row 1 and row 4, and then take minus 3 times the second row and adding it to the fourth row. What I'm doing is I'm starting with my matrix A, and then I apply P, right? That's my swap, and then my add, I take minus 3 and add. That was N. So NPA is the product I would take to compute the matrix that had these row operations applied to it. All right, thank you very much. See you in the next video.